All right, hello. I think we're live. So, welcome everyone to the Convex community call. Today, we're going to be talking about the Sandbox. And with me on the call, I have Rich. You're here on the community Hangout channel.
Hey, yeah, I'm here. This
Welcome,
is going to be
Rich.
exciting.
Um, Anyone who's on the Convex Discord can drop in by the community Hangout channel, and we can chat live on the Discord. Also, if there's any questions, feel free to fire them on the chat, and I will get to them as soon as I notice them. So feel free to fire in with anything at any time. So um, topic for today is the sandbox. And what is the sandbox? So, I mean, the sandbox is effectively a way that you can interactively develop with Convex. And I think I have to show this a bit to really show what it means. But the idea of interactive development, I think, is a very important concept. In traditional software development, you have a code editor. You write code in these source code files, and then you compile that code to make some kind of executable files. And then you run that executable file, and then something happens. And that sort of process is the way that traditional software development has always worked. But for about 30, 40 years, people have been experimenting with different ways of building and interacting with software. And this model of interactive development started to arise, and it's still very important in some areas, and I think it's been growing in prominence more recently. And this is the idea that you actually interact with the software and write code while the system is running, and you can directly interact with the running program rather than writing the code in the editor and going through that entire software development cycle. So the sandbox is an example of interactive development, specifically running on Convex. And it's particularly important in the context of a decentralized system like Convex because the network never stops. The machine never stops running. This is a decentralized virtual machine that will continue to run in an almost unstoppable way with peers decentralized all around the world. So you can't stop the machine and restart it. You're always interacting with this live system when you work with anything on Convex, and that means, of course, that you need ways to upload and deploy new code if you're going to be building smart contracts or other kinds of systems. But it's a bit more than that here. So it's not simply about deploying code. It's actually, well, can you actually develop code live while interacting with the system as it's running? So I'm going to go through some examples and sort of show it a little bit almost by example of what I mean, and hopefully that'll sort of help to illustrate some of the advantages of this kind of approach. So what I have up on the screen here is the page you'll get if you go to the Convex World website and go to the sandbox. And it has a welcome message, and it has some like menus on the left that you can sort of explore some of the documentation and things like that. The core of the sandbox is these two parts of the screen. There's this output window, which is where we're going to be seeing results whenever we execute any code, and this input window where we can input instructions. And this is the interactive part of the sandbox. And it's what in some communities they call a read, evaluate, print loop. It reads your input, it evaluates the input, so it executes it, and then it prints the result. So you see the result of whatever it is you did. So we'll go through some examples of that. Just one other thing to note that's quite important. We will always be working with an account. So in here, it says I'm account number 180. When you come to the sandbox for the first time, it'll give you an option to create an account. So I'm account 180, but if you create a new account, it'll be some different number on the system. There's also a mode of execution on the sandbox. So you can either have a transaction or a query. They sort of do the same thing, except that a query is read only. It never actually changes the state of the network, and a transaction can actually make things happen and can actually update the state of the virtual machine. So you use query if you just want to get information out, transaction if you actually want to make something happen within the world of the virtual machine. So the way I think about it is Convex is this massive multi-user computer. Every single person who has an account on Convex has their own login, if you like, to this computer. Then they can interact with their own environment, with their own little version or little space within this huge virtual computer. So I'm account number 180. So everything I do at the moment is going to be within the context of this account 180. And what I can do.
Mike, I'm following along, and I created an account. I'm 181.
Fantastic. Okay, so you probably created one just after me, so you'll get the next number allocated on the test network. So okay. Yes, anyone who comes and creates an account, you will get a new account, and they'll be sequentially allocated in the instance. So in this case, we're running on the Convex test network, and it'll be 1, 2, 3, 4, 5 up to 180, whatever, and as people add them in. So yes, so it should just be one button to get an account, and you can follow along with this and try this out live. So feel free to do so. So the simplest thing to do is, well, okay, what's an example of something we can give as a command? Well, the simplest thing is we can just give a value. Yeah. So if I type in the number 10 and send the number 10, it's going to evaluate the number of 10. There's no particular computation to be performed on the 10. So it's just going to come back with a result of 10. So you see in the output of the sandbox, the source code that I entered was 10. It evaluated the number 10 and it came out with a result of 10. So if you put in just a value into the sandbox, it's just going to come back with the same value. And there's lots of different values that can exist within Convex. So numbers are a good example. So the number 10 is an integer value. That just gets interpreted as an integer. It supports big integers. So a big number like this is absolutely fine. Yeah, that would overflow if you had a normal 32-bit integer in a programming language. But because Convex supports these big integer types, you can have large numbers if you desire. You can also have fractional numbers. So 1.5, for example, is a floating point number. So the result of 1.5 is 1.5. These are 64-bit IEEE, IEEE 754 floating point numbers. So it's all following all the sort of the floating point mathematic standards. That's 64 bits of precision, so pretty much enough to do any sort of modeling or analytics or mathematical calculations, differential equations, all of these kind of things. You've got enough precision that you can do those to a pretty high level. Other values, of course, it's not just numbers. So you've got Boolean values. So true is a value. Likewise, false is a value. And these are just what you'd use if you're doing conditional statements or Boolean logic. And something which is a little bit different is keywords. So a keyword starts with a colon and then followed by some characters, something like that. Doesn't really matter what word you use. Anything that starts with a colon and followed by alphanumeric characters will be interpreted as a keyword. What are keywords good for? You can sort of use these as labels. So if you want a human readable label for something, whether that's for a field name or some data within a data structure or just some kind of enumeration, where you've got different types of possible values, you can use keywords to give these whatever names you want. So keywords are a nice, useful facility in the language.
Hey,
So
Mike,
yep.
when I first started, I typed OK and I got a error undeclared. So it didn't just take anything, but I just tried it with the colon and I did get the nil.
If you did colon OK, you should get back the result OK.
Yep, I did. I
Yep.
got OK and
You
then it
get
said,
OK back. Yeah. So that's a
yep,
keyword. So colon OK is a keyword and it just evaluates to itself.
yep,
If I do that without a a a a colon, so thanks, Rich. You've just discovered something, pretty fundamental here. What happens if you take away the colon or forget the colon? That's actually going to give you an error. OK is undeclared, and this is intentional, yeah, because without the colon, OK is the name of something. It's just a name for OK. This the letter O and letter K is just interpreted as a symbol. If you put in a symbol and evaluate a symbol, what it's going to do is try and look up the value that that symbol is associated with. But currently we don't have anything called OK, so it's going to give you this error that OK is undeclared. And this is a very important point. A symbol is used to refer to a value in the environment, yeah, as opposed to being sort of a value itself, like a number would be or a keyword would be. If I actually want the symbol itself as a value, I can put a single quote in front of it and OK, and that actually does evaluate just to the symbol OK. So you can quote the symbol in order to avoid trying to do the lookup, if you want to just use the symbol directly. But let's say okay, so great example. If we actually want OK to be declared and to refer to something, well, we can do define, yeah. So I've just put in a def. Def is short for define. It's something you tend to do quite a lot, so we have the shorthand for it. I'm going to define OK, let's say, to be the number 1, 2, 3, 4. Yeah, and I'll explain a little bit about why we put the brackets in later, but you need the brackets, the regular brackets around this thing. So it's def space OK. So OK is the thing we want to declare, and then 1, 2, 3, 4 is the value we want OK to refer to. I execute that. Okay, that seems to have been successful. And now if I type OK, I get back the result 1, 2, 3, 4. So OK is now the symbol OK is now referring to the value 1, 2, 3, 4. So it's like in a dynamic programming language where you create a variable. You can think of it a little bit like that. You're creating this symbolic name for something that you want to hold on to and use later. And these symbols are yours. Yeah. So I'm in account 180 right now. OK means the value 1, 2, 3, 4 in the context of my own account, but it could mean something different in someone else's account. I can't change the variables in someone else's account. Yeah, important for security and important for consistency. You're always in control of the variables and the values that you define when you're programming on Convex and when you're using the Sandbox specifically. So that's the example of defining effectively a value in the environment that you can then come back to and use later. And this is going to be important because we start doing more sophisticated things in the Sandbox. We'll want to set up various things and structures and code that we can come and refer back to later. Okay, so we've talked about some of the basic values. We've talked about a symbol and how that symbol can refer to a value in the environment. Next really important thing is data structures. So what's a data structure? A data structure is, if you like, a composite value. So it's a type of value that consists of subvalues or components. Yeah. So the simplest data structure, or the most common data structure you're likely to see, is what we call a vector. a vector is just a fixed length uh, sequence of values. So we designate vectors in the sandbox with these square brackets, and you can put whatever values you want in here, separated by spaces. So if I put a vector with the values 1, 2, and 3, that the result is, again, it just evaluates to itself, but that is a vector. It's got the value that starts with the value 1, has the next value is 2, next value is 3. Doesn't have to be numbers. I can easily put a keyword in there. Yeah, so 1, 2, hello is perfectly valid as a vector. Why do you use vectors? A couple of reasons. They're very efficient. They're very memory efficient, so they can store the data. You might want to store a lot of different values, and they're very compact, memory efficient, and they're also fast. So if you want to look up values in a vector, you can look them up by position. It's got very fast random access sort of capabilities. And it's often quite concise as well. So from a notation syntax, just creating a vector with whatever you want inside it is a good concise way of expressing some data. So vectors are sort of probably your go-to data structure that you're likely to want to use. Another example of a data structure would be, I mean, you can also think of it as just a single value if you like, but a string. So a string is effectively a data structure which is a sequence of characters. So a string, you just have the double quotes around it. So just like in most programming languages, a string is a immutable value that contains some text. So in Convex, strings are pretty much arbitrary UTF-8 text. So that's an important thing to be aware of. You can also have blob values. So a blob starts with an OX and then whatever hex digits you want. So I can do 1, 2, AE, 4, 5, CC, for example. That is a blob, which is just a sequence of bytes. And those can be as long as you want. So you can have big blobs. You can store encrypted data inside of a blob. It's like an opaque set of bytes that you can really do whatever you want with. Blobs and strings internally are very, very similar. Yeah, so a string is really implemented pretty much as if it's a blob of UTF-8 bytes under the hood. So we have the vectors, we have strings, we have blobs. We also have maps. So a map will be very familiar to anyone who's used a language like JavaScript or dictionaries in Python, or a hash map in Java or C#, these kind of languages. So these are just key value pairs. So this is where keywords come in really handy. Yeah. So if I want to say name, let's say Matt, and age 34, yeah, that is a map. So the name key is going to the value Matt, and the age key is going to the number 34. And that is just a data structure. And these are exceptionally powerful. You can build whatever kind of information you want within maps. Yeah. So anything that you can express in JSON, in JavaScript object notation, you can express in a convex map, and you can nest them. Yeah. So if I want to do like some hobbies, he likes maybe golf and football. I've now put the value for hobbies is now the a vector. So you've used a vector to express a sort of a list of hobbies. And again, that's just so you can nest these to arbitrary length, and you can build pretty big data structures. These are again super efficient. So you can have very large you can have very large maps in Convex, even larger than your system memory if you want, and you can look up very quickly, and you can modify them very efficiently. So they've got all these efficient update logic in the implementation, so you can use them basically to implement databases or to implement quite complex programs with hierarchical data structures as you wish. And this is true of all data structures, by the way. So I can put vectors inside vectors. I can put maps inside vectors. I can put strings inside maps inside vectors. You can compose them in any way you want. So in that sense, it's a fairly flexible data model. So just to show that kind of thing. The last data structure I'm going to mention, and the reason I mention it is because of it's kind of interesting. A lot of languages sort of don't have this natively, but we do have in Convex because I think it has some very useful applications. Is sets. So a set in Convex, it looks a bit like a map, except you put a hash sign before the curly brackets, and a set is basically an unordered set of values, and it's unordered unique set of values. So I can have a set containing the numbers 1, 2, 3, but notice when it prints it out, it's actually changed the order. It's changed the order to 2, 3, 1. Yeah, and that's because sets are unordered. It doesn't matter what order the values are. It's kind of irrelevant to the set. In fact, it'll display them in the order of their cryptographic hashes. So the ordering of set values is basically determined by a hash function under the hood. But that's an implementation detail. From a programmer point of view, or from interacting with Convex point of view, it's just a set of values that are unordered, and you don't really care on the order. Why do we have sets? Well, it turns out that they're super efficient for certain kinds of things. Yeah, if you want to say who's included in a group of people allowed to vote, if you're trying to transfer sets of unique items, like for example NFTs, or if you're trying to do logic with sets, you can calculate the union or the difference between two sets. A lot of this works very, very efficiently. So sets provide this extra capability that is quite powerful, and many languages have sets implemented as a library, but I mean Convex actually has it built into the core runtime capabilities, which I think is relatively unique. If I try and put in a duplicate value, you'll see that it removes the duplicate. Yeah, so I put in a value 3 twice, so we only get one copy of the 3 if you want to create a set with multiple values. So it deduplicates automatically. Okay, so that's a sort of quick overview of the data types and values that we're typically working with, and this is enough to be able to produce pretty much any software you want. Yeah, you've got binary data, you've got booleans, you've got numbers, you've got therefore mathematics, you've got data structures. Anything you want to do to build a fairly sophisticated application can be done just by putting together these different underlying values in various different ways. So how do you actually make something happen? How do you make stuff happen with these values? It's not just enough to store the raw information. We want to actually execute code. The way that we do this in Convex Lisp is using functions. It's a functional programming language, and everything is an expression where a function is applied to some arguments. Yeah, and it's best doing this with an example. But there is a function called plus. This is basic addition, and I'm going to put some arguments to the function plus. So if I put the arguments 2 and 3 and execute that, it's going to apply the function plus to the argument 2 and 3 and get the result 5. Yeah, so it's a mathematical function. And the way that I think one of the beauties of Lisp is it has this very, very simple syntax. And it always works the same way. There's really no other syntax to learn other than the fact that you have your brackets, you put the function you want to use first. So let's say the multiply function, and then whatever you want to apply that function to after. So I can do 10 times 20 times 66. Execute that, and I get 13,200. Yeah. So it's always the same pattern. You put your function first, and then you put whatever arguments you want after that. Why do we do that? One of the most important reasons is it makes the syntax very, very consistent. Yeah, because the function's always in the first place, there's never any ambiguity. Now, if you've ever been confused about operator precedence, or maybe seen people confused by operator precedence, does a plus come first? Does a multiply come first? Does a power come first? If you write mathematical functions in the way that we're normally used to doing them, there's a lot of ambiguity. And we don't want ambiguity when we are specifying software for economic systems, which is what Convex does. We want to be very, very clear precisely the order in which things are happening and which things are happening first, and therefore what the result is entirely deterministic. So we want that consistency and lack of ambiguity. And so we always put the function first. We always put it in brackets like this, and there's not really any exceptions to that. It's you basically now learned Lisp. That is it. That is the entire syntax of Lisp programs is brackets, thing you want to execute first, and then the arguments to that thing afterwards. So yeah.
Boy, that feels very simple, Mike. Not being a programmer, I wonder why people use harder languages.
I think it's largely familiarity. So I mean, if you think about it, I mean, let's say you're doing some Java, and I'm going to type some Java in here, but you can do system.out.println hello world. That's some Java. Except in Java, you'd have to put a semicolon at the end because you have to, because of these ambiguities in syntax, you often need to put delimiters like semicolons to make it clear where your statement ends. You'll notice that this actually has more syntax than Lisp. Yeah, you've still got two brackets around the argument list. But you also have a semicolon at the end, and there's these dots are really just is scoping, but there's at least 3 characters of punctuation around the things that matter, which is the function and the argument. Yeah. Whereas the equivalent in the equivalent of that's obviously going to fail in Convex Lisp, but if I do print, yeah, there you are. So it's actually less punctuation in Lisp, and it's also consistent. Yeah. So in Java, you would do something like 1 plus 2 and your semicolon. Yeah. So you're putting the function in the middle of the arguments. So Lisp is simpler. It has simpler rules and more consistency. On the other hand, it is a little bit surprising. Yeah, so if you're used to writing, mathematical formulae in longhand on paper, the way that Java or JavaScript or indeed most languages do it, basically emulates mathematical notation where you put the operator in the middle between the arguments. Now, if you think about it, it makes more sense to put the operator at the beginning because in many cases you're going to have more than 2 arguments. Yes, if I want to add 2, 3, 4, and 5, yeah, Having 4 arguments to addition makes perfect sense. Logically, that makes sense. You'd want that to work, and of course, it works. So that um, that uh, that model of putting the function first and then a list of arguments that can be of potentially arbitrary length is a very simple, clean model that kind of applies generally to everything you might want to do. Now, obviously, if you want to do that in Java, you'd have to go 2 plus 3 plus 4 plus 5. Yeah, so you'd have to actually include the operator multiple times to make something like that work. So it's style, it's syntax. It doesn't change the meaning of what's being done, but the Lisp way of doing things is simple and quite elegant. By the way, there's no reason we can't make this style work on Convex. So the Convex virtual machine will be able to execute that just fine. It's purely the syntax of the language we use in the Sandbox is Lisp, because it has these nice properties and sort of benefits to how we like to do it. So notice though that all of this stuff I've been running, that's running on the live Convex testnet. All of these instructions are being executed by the Convex virtual machine on the testnet, and I'm getting these answers back basically instantly. I mean, you wouldn't really notice that you're running on a decentralized network as you go through these things, but of course we are running on a decentralized network. I'm running in this account 180. I have some balance, so I can check my balance. So we have these little stars, or some people call them earmuffs, around a word, are some special words that can be used to access some features of the system. I can see that I've got some 99 million convex coppers in my account, which is just some coins I can use to execute some transactions and sort of do the demo. The Sandbox also sometimes helpfully gives you a bit of a description of what you've just done. Yeah, particularly when you type in a single function, it gives you a bit of help text, which describes what the balance function does, as well as telling you the result. So every time we execute a command, we're actually using up a small amount of these convex coins, but super efficient. It's effectively free, but just to be aware that these are real transactions going through a real decentralized network at this point. What we can do, of course, is we can do instructions that actually make meaningful changes to the network that represent economic systems that we want to execute. So within the functions that are available built into the system, there's lots of functions which have some kind of economic meaning. Yeah. So transfer is a good example. If I just type transfer address amount, this is going to transfer some coins to the target address, and it will return the amount transferred if it's successful. So again, same syntax. Yeah, I just say I want to transfer, and thanks, Rich. I think Rich, you said you were 181, so I'm going to give Rich 10 million.
Oh, awesome! I appreciate that.
There you are. So 10 million. Just check I've got the right number of zeros. Okay, so that looks like it succeeded. It didn't show any error, and it returned the amount transferred. And now if I check my balance, you'll see that my balance has just dropped down to 8.9 million. So I've 10 million has gone out of my balance, and a little bit more on the sort of the transaction execution cost. So in just one line of code, you can execute economic transactions, instructions on the network. And this is why I think interactive development is so compelling for systems like Convex. If you are,
when I do balance, I got 10 million more.
You got 10 million more. Well, you should, yeah. So the
Thank you.
coins can neither be created or destroyed. So if 10 million went out of my account, it must have gone into somewhere else. And luckily, I used the right address, so it's gone into your account. But this is the power of the system. Yeah, you can have an economic transaction in one line of code, just executed instantly and being fully settled. Yeah, and by settled, I mean it's gone out of my account, it's increased on the other account, the total number of coins is consistent, they can't be created or destroyed, etc., etc. So this is the power of this system. If you're a power user, you can do anything you might want to do in the digital economy with just one instruction at a console like this. So yes, the sandbox is a tool for learning and for experimentation, but the same kind of tool can actually be a real operational system. If you wanted to execute, real transactions, you could. And if you imagine a mobile app that was doing transactions, what it's doing under the hood really is just sending a command like this to the network. Yeah. So this is a way just looking beneath the graphical user interface and executing the commands directly, or as close to directly as you can get on the system. So and this applies to anything you can do on Convex. You can do in this way, in this interactive mode of development. So for example, if I wanted to deploy some new a new actor, I'm just gonna just deploy something stupid, but that has created a new actor account. Yeah, so I can deploy some code to create a new account, which would be an autonomous actor, which will be then running on the network. And that's all happened just by issuing interactive command. I didn't go to any external tool. I didn't use any kind of compiler. I'm just instructing the network to do precisely what I want. And this is possible because the network has an on-chain compiler. So it can take the code, it can compile it, and it can execute that entirely on the network. You don't need any external tools, which is, I think, fairly unique in decentralized systems. That there's a full compiler, high-level language compiler capability at your fingertips. And that's what allows us to offer this kind of interactive development environment without any additional complexity. And it really is that simple. It really is just type whatever command you want. It happens instantaneously, and you can access anything which exists within the network as you do that. Now, one thing to note is, of course, it is a public network, so I can see other accounts. So if I want to see Richard's account, I can see the data associated with the account. I can see that he's so the sequence 17, so he's probably executed 17 commands. His balance is 10.9 million. So he's obviously received the coins I sent. He's defined a value of OK. He hasn't specified any additional metadata. He doesn't have an account controller, and he has this particular public key. So obviously I can't see the private key because everyone's private key should be private, but you can see the public keys of accounts on the network. So that is an example of what you can see all of this on the network if you want, with just querying the account information.
Hey, Mike.
Yep.
Mike, I was trying to transfer you back, and because I was not actually watching the screen, I didn't remember exactly how to do it. But I found there's this thing called show examples.
Yes, there is. Yeah. So there's a bunch of things here just for like convenience, but there's an example and reference. It's got a list of all the built-in functions, so you can see all the things that are available and a little bit of documentation which describes them. So there's a lot. There's a lot of functionality available on the CVM that's accessible This is the core library. There's other libraries as well, but the core library functions are basically what you need to do everything else. So that's the core library, and then you can see actually there's some documentation for some of the other languages as well. So
So I'm trying to send you back 10 million, and I would do earmuff, transfer, earmuff, and then straight bracket.
It's brackets. So what you want to do is transfer like that with brackets. So no earmuffs on this. Why is there no earmuffs? Because this is a function. You're applying a function which is the transfer function, and the transfer function wants two arguments. First of all, it wants a destination. Who am I transferring to? And then the amount that you want to transfer to them. Yeah, so I can send 5 copies. So that would send five copper coins to you, Rich. So same model, same pattern, and if you ever want to know what the functions do precisely, you can always go and find the transfer function in the reference, and it'll give the description. It'll also tell you what parameters it needs. So transfer in this case needs an address and an amount.
Yep. Okay, I transferred back the 10 million to you.
It looks like you have indeed. I see that 10 million's gone out of your account. So perfect. So that's it. I mean, that's all you need to do a transfer.
It's pretty easy once you know it.
Yeah, and that's why I was keen to do this, because I mean, a lot of people have asked about the sandbox and how does it work, and how to get started on developing things on Convex. So I thought it's just really to go through and show how simple it is to do some potentially some quite powerful things in the sandbox.
Can you check your account to see if the 10 million got there?
Sure. So I can check my account, which is 180. And yes, I've got my 10 million back. I can show another trick. So whenever I want to refer to my own account, I can use this earmuffs address, and that will always return your current account. Yeah. So in my case, it's going to be 180. So anywhere if you don't want to remember your account number all the time and type it in all the time, it often makes sense to just refer to address like this, and then it just substitutes it in and refers to your account.
I guess that'll get important when there's really long account numbers, maybe.
Well, I mean, it's more safety. It's easy to see that address is referring to your own address. If you see a long number and one of those digits has changed and you don't realize it, you could easily end up sending things to the wrong destination, or you could end up trusting an account that you shouldn't trust, these kind of things. So it's safer to use an explicit term than it is to remember magic numbers that you may get wrong, or that someone may try and trick you into getting wrong. So that's the primary reason for that. It's not really about length. We don't really care about saving a few characters of typing. We do care a lot about security and making things very, very clear and obvious. So good code, if you're referring to your own current account, you should always use address in this way.
Got it.
That makes sense.
Now you can make your own token on here too, can't you?
Yeah, so good example. So that's an example of a library that we could use. So let's talk a bit about what it means to use a library. Yeah. So the core library in Convex is the one that's already available. Yeah, it has all of these functions like transfer. Yeah. So there's a whole bunch of built-in functions that you can use straight away out of the core library. However, this is programming. People are always going to want to develop new functionality. They're always going to new features, new capabilities, new tools, etc., etc. So just having the core library isn't ever going to be enough. We're always going to need to pull in additional software and additional tools and additional libraries. So how do we do that? Well, what we do is we use this function called import. And import lets you pull in a library from the network. So someone's uploaded or pre-created a library on the network, and they've registered the name of that library, and you can then use it by importing it. So if I do import, let's use the fungible library is a good example. So convex.fungible. This is the library which you mentioned that we can use to create fungible tokens, and I've spelt it wrong. You import it, and you can give it an alias when you import. So I normally call this fun, yeah, just because it's short for fungible, and it is also fun to play with. So what this is going to do is it's going to create this alias fun, which refers to the library. So if I execute that, it's returned the result 13, and the Sandbox has helpfully told me that this is in fact a library. Yeah, that I've pulled in this account number 13. If I type in fun now in the Sandbox, you'll see fun just refers to account number 13. Yeah, it's like a pointer saying anytime I use fun, I want to reference account number 13. Now, this is good practice, and it's good practice because you always want to give things explicit names. And again, it's about security. You don't want to be using magic numbers like 13. You want to be referring explicitly to this particular library that you want to use and nothing else. Yeah. It is a security risk to go and use library code that's untrusted. So you should always be very careful when you import something that you know what it is that you want to use and why you want to use it. So I've imported the fungible token library. So now if I want to create, let's say, a fungible token, I want to tokenize some newfangled asset that I've invented. I can use the deploy function. So I'm going to be deploying a new actor to implement this fungible token. And I've got to deploy some code. And the fungible library has a function within it called build token. So fun/build token is the way that I refer to the build token function within the fungible library. Yeah, so slash is like almost like a just helping to narrow down the location. And the build token function takes some parameters, but the most important one is if I want to say supply, and I want my token to, let's say, have 999 tokens when it initially gets created. So I run that, and it's created a new account. The new account has address 183, and the type here is an actor. So an actor is an autonomous program which is going to be managing our fungible token. Now I should be able to do, again, using the balance. There's a balance function in the library. So now I'm not talking about my balance of convex coins. I'm talking about my balance of the fungible token. So I'm using the balance function within the fungible library. And I'm interested in my own. I'm interested in the token 183. Yeah, which is a fungible token I just created. And again, I'm using address because I want my own balance. And you can see there that the result is 999. So I've just created this token. This is the equivalent of like an ERC20 token kind of model with a supply of 999, deployed it as an actor, and then again I can use the fungible library to check the balance, and I can see that my balance is 999. If I want to transfer some of those coins, for example, to Rich, I can't remember which order the arguments come in, but let's just see. So the transfer function, token target amount. Okay, so I can do fungible transfer. I want to use the token 183, which is the one I just deployed. I want to send it to the account 181, which is rich. And let's say I want to send 10 tokens. Okay, I think that's worked. So it's returned 10, which would be the amount of the transfer. Let's just double check my balance. Yeah, I'm now 989. And if I check the balance of account number 181, which is rich, he's got 10. Yeah, so it's worked. So we have a fully working token implementation. And notice I didn't have to write any complicated code. All I had to do was import the library that I wanted to use. So with this import function, and then I had to call one build token. I had to deploy one built token using this command here. So again, you could do some quite sophisticated things. I created an entirely new digital asset with a supply of 999 that's got all the capabilities of a fungible transferable token, and that was just one line of code. And I can do all of this at the sandbox. Yeah, I don't have to write any complex code in external tools and do any fancy expensive deployments. It's just all at your fingertips, which is why I think it's quite fun to develop at the sandbox. It just, you can get this sort of interactive feeling of seeing what you just created.
And Mike, when we go live with the ProtoNet, it'll work the same way or what?
Yes. So all of these capabilities will be live on the ProtoNet. So this is testnet at the moment. It's good for developing. It's good for experimentation. It's good for trying out new things. But none of the coins or the assets on testnet are real. Yeah, it's all for testing purposes and for development purposes. When we go live with ProtoNet, it will be real. So the Convex coins will be real, and any digital assets that people create, any fungible tokens will be real and live. So other than that, it works the same way. Yeah, it's the same underlying technology, the same underlying software, consensus network, all operates in the same manner. So all of these capabilities will be live on day one with the ProtoNet launch early next year.
Okay, I got a question. Earlier you wrote some Java code or something like that, Python or whatever. If somebody was like stuck in that kind of programming mode, what would have to happen for them to be able to write that and it work in Convex? Would they need to call a library or something?
In terms of having the syntax of a different language.
Yeah, yeah.
We do support multiple language front ends. So you could have, in fact, one of our contributors actually made an experimental language, Convex Script, which was basically a JavaScript-like language running on the CVM, which absolutely works. So you can create other language front ends with different syntaxes and compile them, and they'll just compile to the CVM, and you can then use whatever syntax you like. So there's absolutely nothing to stop people from developing or using different syntaxes on the CVM. Now we happen to use primarily Convex Lisp at the moment. It is a very powerful language. It does have a lot of powerful capabilities, so we like using it. But it's totally fine if someone wants to use a different language front end. That's also absolutely possible. Currently, we do have a couple of experimental different language front ends, but not actively developed and not sort of actively got a big code base in them. Yeah, so it's very much, if you want to experiment, it's a great place for a hacker to have some fun, but it's not sort of developed to the sort of prime time yet. So currently only Convex Lisp is sort of I'd say well developed and maintained and supported, but the possibility is endless. on that thing.
How does it live? Does it live in infamy forever as that script language the guy wrote? Does it become a library? What does?
So
How,
so the library itself, the script language is actually it's a front end, so it runs off chain.
okay, gotcha.
Yeah, so
Okay,
a client can implement whatever front end they want, um, and compile down to CBM instructions. And as long as you can compile down to CBM instructions, you can do whatever you like in the front end. And so in
got
fact,
it. Okay,
this Convex Lisp does the same thing. Yeah, this just gets compiled down to some lower level CVM instructions, which then get executed. Um, it just happens that the Lisp tends to be a very simple language to compile, and quite an easy language to compile fairly well. So it makes it easier for compiler writers or front end writers to be using something which is Lisp like. But yeah, you could do anything you want on the language front end. You could even have a visual front end, drag and drop boxes and connect them together with arrows, and nothing stopping you doing that and compiling that to the CVM as well. It's just a bit more engineering to get that interface all up and running.
okay. I got
Um,
another question. You did this fungible token in a line of code. What would that look like if I was trying to build one on Ethereum?
uh,
Would I need to write a smart contract, or
yeah,
how
I
does
mean,
that
you'd
work?
probably use something like Open Zeppelin.
Okay, what would?
So uh, Open Zeppelin has a whole bunch of code that lets you create tokens, ERC20. So I want to. Uh, it's got some nice tools. Yeah, this is Open Zeppelin. So this is an ERC20 token source code. It's using a bunch of Open Zeppelin libraries. It's extending, so Solidity is a bit more object oriented. So there's a bunch of inheritance going on. So it's inheriting a bunch of code from all of these other places, and then it's writing this code for you. So it's got a bit of a code generator. You would then have to compile that and then deploy that um, to Ethereum or an EVM compatible network. There's obviously security risks at various places among those supply chains. I mean, that's quite a lot of stuff to audit. And if your tool chain is compromised when you're deploying the contract, someone can do a code injection. No, there's it's a lot more complicated, basically. Um, so I mean, I think you can generally do in Convex in one line what would be a mini project on most other systems. So
Wow.
we like the term one line DeFi. Sort of any reasonably sophisticated economic transaction you ought to be able to do in one line of code on Convex. And if you can't, then we'll have a think and we'll figure out how to do it, because it generally, so far we've not found anything that we can't do in one line of code, with some appropriate thought about the uh, nature of the interfaces and the contracts and the constructs that are being used.
So you pulled up an actor to do that. Uh, is there a whole library of different actors?
Um, so I created an actor to implement the fungible token. So this was the 183. This token I created. If I type in just 183, the address, you'll see that this is an actor, and I can actually see that there's some functions within here. So accept, balance, check transfer, get offer, offers, quantity adds, supply. Oh, you can see my supply is 999 there. That's nice. So this is actually looking inside the actor to see what functions and code exists within that actor. Um, That's all implementation detail. I don't need to know that to know that it's a token that a token I can use. But all of that got generated by this single line of code. Yeah, this deploy build token with the token supply. So these are all the capabilities that it offers. Now, that's a specific kind of actor. That's an actor which implements the fungible tokens. Now, there's a whole bunch of different ones. So there's some of them are documented here. So I've got some. There's ones for NFTs. There's the boxes. So that's a digital asset that you can put different assets inside it and move it around as a box. There's a trust library which has a lot of functionality for authorization and governance. There's a registry which is like a name system, got the name, supports the name system and various other things. So there's a bunch of different libraries available on Convex. You can of course write your own. There's nothing stopping any user of the network from developing their own libraries. They're just some things that we've created and deploy for convenience. But yes, there's libraries for all sorts of different things, including decentralized exchange. If you want to have an exchange, trade tokens, various different kinds of smart contracts, etc. So a lot of this is already built, and if it's not already built, it's usually quite quick. Yeah. So writing your own actor in Convex is relatively simple. There are obviously subtleties when building these kind of things to be secure, but it's certainly, in terms of the amount of code you have to write, it's pretty minimal in many cases.
Well, that's awesome. I think we're at the top of the hour.
Yeah, I mean, I would love to go into more on this and how to actually build an actor and how to actually write some smart contracts. But I guess we'll have to save that for another time. But hopefully, that's given everyone a taste of what's possible in the sandbox and why it's very powerful to have this kind of interactive capability right at your fingertips.
Yeah, maybe the next community call we can expand it to writing an actor.
Yeah, I'm totally up for that. Let's write some smart contracts and get the network to settle and enforce them, because that's what you really need if you want to build these decentralized open economic systems.
Awesome. Thanks
All
so
right.
much.
Well, thanks everyone for joining.